my function is e to the x, so y1 minus y2 over x1 minus x2. And like the sine and cosine proofs, and unlike the polynomial proofs, I'm kind of stuck with the polynomial ones. We could factor. Factoring was what saved us. I can't factor here. But there is a nifty little algebra trick that cleans this up pretty quickly and gives us our answer. If I multiply the top and the bottom by the same thing, okay, again, you can't just multiply the top or just the bottom. You have to do both. That way you're multiplying by 1, and multiplying by 1 still keeps this equal to what it started with. But it's a little convention that will turn it into something that we can work with. So I'm going to distribute through the numerator. The denominator, I'll just leave it as e to the minus a, x minus a. But the numerator, I'll distribute. So I'll get e to the x times e to the minus a minus e to the a times e to the minus a. And I know that might look a little messy, but our rules of exponents always apply the same way. If I have x squared and I multiply it by x to the 4th, that's an x to the 6th, okay? So I add my exponents. And if I add my exponents, x plus negative a is x minus a, and a plus negative a is what? 0. So I get e to the x minus a minus 1 over e to the minus a times x minus a. And I'm going to break that up also. Okay, so in it, again, there was a kind of a connecting concept between the last two proofs for sine and cosine and this one, in that little algebra trick gives me some limit form that I can investigate, and the second factor ends up equaling 1. Okay, I'm pretty certain if you go back through all your notes about limits, we looked at that form, but if we go back to our calculators right now, and I type in something like e to the x minus 1 divided by x, and we let x go to 0, from our table here that as I get really, really close to 0, my y's are getting really, really close to 1. Alright. So this turns into the limit as x goes to a of 1 over e to the minus a times 1. Okay, so again, this is just equal to 1. Okay, I just used my calculator to show that if I have this exponent matching this denominator, if this exponent matches this denominator, and I have e to exponent minus 1 over the exact same exponent, and the exponent and the denominator are both going to 0, that my limit is 1. That was what I was showing on the calculator. So I'm basically done because this has no variable in it anymore if you think about a being some specific x, but rewriting 1 over e to the minus a that's the same as e to the a. So interestingly, e to the x is the only function whose derivative is itself. I mean, that's what we just proved. We just proved that if I find the instantaneous slope, I end up getting itself. So the rule for e to the x, if f of x is e to the x, its derivative is also e to the x. E to the x's derivative is itself, and it's the only function that's true. If you think about e to the x's graph, it makes sense. Again, all of these little graph proofs are not finalized proofs, it's just, it kind of supports what we found. But here's the graph of e to the x, and think about my slope. My slope is almost 0, but as I move to the right, my slope gets steeper and steeper and steeper and steeper and steeper and steeper and steeper. So if I draw a picture of that, this is almost 0, but then as I move to the right, my slope gets steeper and steeper and steeper and steeper and steeper. I get the same graph. Okay, that line on your checklist had a to the x where your base is some other base besides e. I'm going to hold off on that also until we talk about the chain rule.